Year 13 PPE2, this is Pure Mathematics 2 hours, first question. This is about the Factor Theorem. Okay, we've got to find the value of a in this function here. So we're going to substitute x with the number 1 and set it to 0. And we've got to show clearly our method. So f of 1 is equal to a times 1 cubed plus 10 times 1 squared minus 3 times a times 1 minus 4, and that is equal to 0, which means that a plus 10 minus 3a minus 4 equals 0, and a quick bit of rearrangement of that gives us that minus 2a is equal to minus 6, and therefore a is equal to 3. Okay, so a nice straightforward question to start with. Number 2, this is about functions, and what we have to do here first is state the range of f. It's only 1 mark. Look at this, you can see that the minimum value of 2x squared is 0, because you're squaring something, which means that the maximum value of f of x is 7. So all I need to do is say that f of x is less than or equal to 7. You must put the including as well, because it can be 0, meaning that that can be 7. Okay, part B, this is about composite functions. So I'm combining the function g with f. So I'm finding this, I'll just do it in one go. I'll start writing the function g down, which is 3, and then x, but instead of x I'm going to write what I would get if I put 1.8 into f, which is 7 minus 2 times 1.8 squared. Okay, so that square bracket is replacing my x in here, and I've got to use the same square bracket again with the 5 next to it here. So I can just quickly take a copy of that and put it down there. Okay, and that goes underneath there. And from the end of that, I've just got to take away minus 1 here. Put my fraction line in and put that on the calculator, and it comes to 39 over 40. Okay, that's the answer to part B. And for part C, I've got to find the inverse function of g. Well, the way to do this is to set y equal to that function g and then rearrange it to make x the subject. So y equals 3x over 5x minus 1. Multiply both sides by the denominator. So I could go to writing 5xy minus y equals 3x. Okay, and then I put all the x terms on the left, so I've got 5xy minus 3x, and the non-x terms on the right, which is just y, and then factorize out the x. So I now only have x appearing once in the whole equation, and then I can just divide both sides by the bracket. So that gives me that x equals y divided by 5y minus 3. Okay, and then finally I just rewrite that in terms of g to the minus 1 of x which is the inverse function, g to the minus 1 of x, and then replace the y's with x's here. So that's x over 5x minus 3. Okay, and that's it. Next question. This is about logs. Okay, I've got a log 3 there, a log 3 there, and I've got a number here. Don't want a number. What I want to do is write that as a log 3 as well. So it's going to be log to base 3 of 9, because 3 to the power 2 is 9. And now I've got everything in terms of log 3. So I can now say that log to base 3 of, and I'm going to make a fraction by using the rules of logs with the minus sign there. It means I've got 12y plus 5 on the numerator, and underneath that 1 minus 3y. Okay, that's a fraction, and the log of that to base 3 is going to equal log to base 3 of 9. And I can take the logs away now and multiply by 1 plus 3y at the same time, I think. So I could say that 12y plus 5 is equal to 9 times 1 minus 3y. Multiply out the brackets. 12y plus 5 is equal to 9 minus 27y. Rearrange that to give me 39y equals 4, and therefore y would be 4 over 39, and that's the answer. Okay, next question. Now we have here something, we've got to use this small angle approximations. When you get questions like this, try to use the approximation for sine, which is easier to use because basically sine theta approaches theta as theta gets very small. So I'm going to actually rewrite this cos squared as 1 minus sine squared first. So I'm going to write 4 sine theta over 2. Okay, and then plus 3 1 minus sine squared theta, and then I'm going to say that that is approximately equal to 4 lots of theta over 2 plus 3 minus 3 theta squared without the sine, you see. And if I just well, that's virtually it. I've just got to simplify that a little bit, and in fact change the order as well. If I write it as 3 plus 2 theta, just swapping the first two terms over, minus 3 theta squared, it's now presented in the order required here. So I can see that A equals 3, B equals 2, and C equals minus 3, and that's it. Okay. Next question. This is about recurrence relationship, where one term of a sequence is defined in terms of a previous term. So what we're going to do here is we need to show that this result is true, and it involves knowing U1, U2 and U3. Well, we know what U1 is because they tell us here. So what's U2? Well, we'll find out. U2 is going to be U2 is going to equal it's going to be k minus 24 over 2, okay, which is k minus 12. So that's the second term of the sequence. Now to find the third term, U3, I'm going to do k minus 24 over u2, which is going to be 24 over k minus 12. Okay, and I'm now going to just put that with a common denominator of k minus 12. So that's equal to k minus 12 minus 24, okay, all over k minus 12. It may not be necessary to do that, but it's usually better in these sorts of problems. We'll see in a moment. Okay, so that's my term for u3. Now what I'm going to do now is I'll just multiply this bracket out. So I've got k squared minus 12k, k squared minus 12k minus 24 all over k minus 12. Okay, so that's my expression for u3. So if I apply this, I'm just going to put a line to indicate what I'm doing there. Okay, so that's coming from this here. So u1 is 2 plus 2 lots of u2, which is 2 lots of k minus 12. Okay, and I've also got to add u3, which is what I've just done here. Okay, k squared minus 12k minus 24 all over k minus 12. And I know that that has got to be set equal to 0. Okay, and that's going to enable me to find k. Okay, a bit of working out there to do and so forth. I'm going to take everything, multiply it by k minus 12 now. So I'm going to have 2k minus 12 plus 2k minus 12 all squared plus k squared minus 12k minus 24. Okay, now if I work on that a little bit further, it gives me, let's have a look, quite a few steps to go here, so let's just go through the whole thing. I think 2k minus 24 plus 2 lots of, well, it's going to be k squared minus 24k plus 144 and plus k squared minus 12k minus 24 equals 0, and that works out to be, I will take a few steps. Oh no, I've got to show it, so really I should put the steps in actually, so don't be tempted to shortcut too much. I will just go a bit further with this. 2k minus 24 plus 2k squared minus 48k plus 288 plus k squared minus 12k minus 24. Now I need to really start gathering terms together now. So I've got 3k squared and in fact at this point I can see the rest of the result. So 3k squared minus 58k, okay, plus 240 equals 0, which is the result I had to prove. Once you've got to the stage of separating out all the brackets, multiplying them all out, combining terms together usually enables you then just to jump straight to the conclusion. But don't do it too soon, because it does say show that it's true. Okay, so we've done it now. And we've got to find the value of k, giving a reason for your answer. Now that suggests there are two values, and if you look at that carefully, you can see it will factorize. Okay, so this is part B now. Okay, so part B, it will factorize because the first part can only come from 3k and k. Okay, and in fact it's minus 40 and k minus 6. Okay, so they're both positive values of k. Okay, but it says find the value of k, suggesting there's only one of them. So let me just start by writing what they could be. So k would be 40/3 from the first bracket, or k would equal 6. Okay, now you can cross that one off because it does say that k is an integer here. All right, so it's that one that we need, and we can say k equals 6. So we need a sort of conclusion really. K equals 6 since k is a member of the integers. Okay, that's how I would answer that. And finally, for part C, we've got to find the value of U3. Well, that just means substituting our value of for U3 into substituting our value of k into our expression for U3. So it's going to be 36. Okay, I'm just substituting it into this here, 36. In fact, I could probably use this one here, but I'm doing this one now. So it's 6 squared minus 72. Okay, and then it's minus 24. And all of that is over minus 6. Okay, and that comes to exactly 10. Okay, question done. Number 6, we can't use calculator technology. Well, we can, but we need to show solutions. So this is about ultimately about geometric sequences and series. So let's have a look at what we do here. We've got to show that so at the end of year 1, in its first year of trading, year 1, the company made a profit of 20,000. The model for future profits is that they increase by 8% a year. So for the end of year 3, it'll be 2 years worth of profits at 8%. So what I need to do for part A is simply start with 20,000 and multiply that by, increase that by 108% twice over. So it's 1.08 squared. And that comes to 23328. Okay, exactly that. And that's the answer. So I just need to put the pound sign in front. So that is my working, very simple for part A. And part B is wanting me to find the first year when the profit exceeds 65,000. So basically, I've got to do the same kind of thing, but instead of using 1.08 squared, I'm just going to use a power of, say, n for n years. So I've got 2,000, or 20,000 rather, times 1.08 to the power of some number n has got to be greater than 65,000. Okay, and if I just divide both sides by the 20,000, I'll get 1.08 to the power of n is greater than 65 over 20. Okay, which is 13 over 4. And I can now use... Now what I'm actually going to do is I'm going to use n minus 1 here, because the way it's worked, you see this was the end of the third year and we were using 2, so for n years we're better off actually using n minus 1 there, just to keep it consistent. So that's n minus 1, that power there. Okay, and then I can take logs of both sides, and I can say that 1.08 to the power of n minus 1, the natural log of that, I can use logs in any base, but it's easier to use that, is greater than the natural log of 13 quarters. Okay, now I can now use the powers or rule of logs and put the n minus 1 in the front. So I can say that n minus 1 times the natural log of 1.08 is greater than the natural log of 13 quarters. And I can now do a division, and I can actually do this. So I could say that n is greater than, because I can add the 1 as well, so I'll divide both sides by the natural log of 1.08. So n is greater than the log of 13 quarters, okay, divided by the log of 1.08, and from that I've got to add the 1 that I had with the n over here. So I've done a couple of steps there in one go, and that is equal to 16.314, etc. So therefore n equals 17, because it has to be the first integer greater than that, 17. So year 17 is the answer. Okay, year 17. And for part C, find the total profit for the first 20 years of trading. Now, this is a series now. This is the sum of the terms of a sequence. Okay, so what I'm going to do is find the value for the first 20 years of trading. So it's going to be this formula. So the sum of the first 20 terms of a geometric sequence is equal to the first term, which is 20,000, okay, and that's got to be multiplied by 1 minus the common ratio, 1.08 to the power of 20, okay, divided by 1 minus 1.08. Okay, and that's literally just using the formula for the sum of a geometric sequence. And that comes to 915,000 to 3 significant figures. Okay, because it says to the nearest £1,000, which is that. Okay, and that's the answer. Okay, this next question is about derivatives, first and second derivatives, and points of inflection, stationary points as well. So I've just done the graph of this quartic function here. You can do this on your graphics calculator, of course, and that will help you understand the question that you're doing, even though you still need to show sufficient working. So we're talking about a stationary point at x equals 1. So I've just magnified part of the graph here. There's x equals 1. And I've also got to show that that's a point of inflection as well. Well, it is, and you can see that from the graph, but you can also see that there's another point of inflection probably around here where it changes from concave to convex, but we're not being asked about that one. So first of all, let's find dy by dx, and that's a pretty straightforward differentiation here. So we've just got to carefully do it term by term. So we have 20x cubed minus 72x squared plus 84x and minus 32. And the second derivative is just the derivative of that, which is 60x squared, okay, minus 144x and 84. Okay, so part B, verify that C is a stationary point at x equals 1. So I'm just going to say here for part B, 1. Okay, when x equals 1, dy by dx is equal to, when it says verify, you've just got to basically put 1 into that and show that the answer's 0, because we want the gradient to be 0. But you need to just show that you're doing that by writing it down as a substitution. So 20 times 1 cubed minus 72 times 1 squared plus 84 times 1 and minus 32. And that does equal 0, which is what we wanted. Okay, and for part B2, show that it's a stationary point, that it's also a point of inflection. So we put x equals 1 again, and we work out the second derivative. Okay, now I'll just do this first and then explain what we're doing here in a moment. So the second derivative is 60 times 1 squared minus 144 times 1 plus 84. Okay, now that is also equal to 0, and that is a necessary requirement for a point of inflection. So therefore we have that condition satisfied, but in fact that's not good enough on its own. Okay, because it's possible to have a function where both the first and second derivative are 0 at a particular point, but it's not a point of inflection. So what you can do, it's not always reliable, but you can do the third derivative, and if that's 0, then you've got to do further inspection. But if that's not 0, then you can be sure it is a point of inflection. So we'll take a chance with this and we'll do the third derivative, okay, and see what that comes to. And that's just simply the derivative of what we've just done. So it's d3y by dx cubed. Okay, now that comes to 120x, okay, minus 144, and that does not equal 0 when x equals 1. Okay, so therefore I can conclude that at x equals 1 is a point of inflection. Okay, and just to be clear on that, if the third derivative was also 0, you would have to do further testing. The method often used is to simply take a value either side of the point, close to it, and to see what the second derivative of that is, and that needs to change sign in order for it to be a point of inflection. Okay, but this is fine, and that has worked. Okay, and I also should add somewhere up here when I had to verify that it was a stationary point. I just need to confirm that because the gradient's 0, therefore stationary point. Okay. Okay. Right, next question. Okay, we've got a circle. We have an equation there, and it says find the coordinates of the center and the exact radius. Now, you can draw it on the calculator and you can see where the center is. It's here, but you can't just write that down from what you see on the screen. So you need to show that it's the center by doing the completed square form of this. So my first job here would be for part A to complete the square for x and y. So I'm going to do x minus 5 squared. Okay. And then I'm going to have to subtract the 25 from that I would get. And for the y part, I'm going to have y plus 2 squared. Okay, to give me the y squared plus 4y. So y plus 2 all squared, take away the 4. I've still got to add my 11, and that gives me 0. Okay, and now I just tidy that up and put all the numbers to one side, and I get x minus 5 all squared plus y plus 2 all squared. Okay, and that's supposed to be a plus there. And that, if you just move the numbers over, gives you 18. Okay, and therefore, as you should know, the center of the circle is 5, minus 2, as you can see anyway looking at this, and the radius is root 18. So the question 2, well, this is questions 1 and 2. So part 1, I can just now say 5, minus 2. And part 2, I can say that's root 18, which is root 9 root 2, which is 3 root 2 as a simplified surd. Okay, so that's the first question answered. And next I have this straight line L with that equation where k is a constant, and I'm told that it's tangent to C. Okay, find the possible values of k giving your answers as simplified surds. Well, basically this represents a line with a gradient of 3 and it crosses the y-axis at k, and it's telling us that there are 2 of these lines that are tangent to the circle. Well, it's quite clear to see what's going on here. If I took a line with a gradient of 3, okay, that touches the circle, it's roughly going to do something like this. I'm just going to sketch things. It's bound not to be in the right place, but it's about there. That's got a gradient of roughly 3. And then there's going to be another one over here somewhere that's parallel to that. Okay, not very well drawn, but you've got the idea, and that's going to cut much lower down here somewhere. Okay, so I've got to basically find these 2 possible values of k where this line crosses the axis and where this line crosses much further down here. So it gives me an idea of the sort of size of numbers I'm expecting. So let's see what we actually get when we do the algebra for this. So I'm just going to make a direct substitution into my quadratic, and in fact it would be easier to go straight into the original form up here. Okay, so I'm going to replace the y squared with 3x minus k squared. Okay, so this is what I would do. I would say that x squared plus y squared, which I'm now writing as 3x plus k all squared, and that is going to have minus 10x. Then I'm going to have plus 4y, but instead of y I'm going to write 4 lots of 3x plus k again, and then plus 11, and that equals 0. Okay, so I've got to do a lot of multiplying out and tidying up and regrouping. So I might take out a couple of lines of working just for the purpose of this video. So if you multiply all that out and regroup everything, you'll have 10x squared, okay, plus, and then it's 6k plus 2 lots of x, that's in a bracket there. So I've regrouped all the x terms, the x squared terms, and so on, and the constant, which is k squared plus 4k plus 11. Okay, k squared plus 4k plus 11. Okay, I'm going to put that in a bracket, not that I need it there, but it just helps to highlight it as the constant at the end. And for the lines to touch but not cross, I need the discriminant to equal 0. Okay, so delta equals 0, which implies that b squared equals 4ac. Now I tend to put that in speech marks because I haven't actually got the letters A, B and C anywhere. I've just plucked them out of the air, but that's what I'm doing. So basically I've got to set 6, so if I come over here now, 6k plus 2 all squared. Okay, that's my b squared, if you like, has got to equal 40. 40, yes, that's 4 times 10 times the constant, which is this bracket here. So that's got to equal 40 lots of k squared plus 4k plus 11. So it's just a quadratic that I'm going to get in k. I will just take a step out and go straight to the result from that, which is that 4k squared, okay, just for the sake of the video, 4k squared plus 136k, okay, and plus 436 equals 0. There is a factor of 4 that comes out of that to give you k squared plus, now that's 34k, and at the end it's 109. Okay, now that doesn't factorize, okay, but it does solve with the quadratic formula, or completing the square if you wanted to, but quadratic formula is easy enough, and it does say give your answer a simplified surd, so that's a bit of a clue. And from that you get k is minus 34. Okay, k equals minus 34 plus or minus the square root of 34 squared minus 4 times, so it's 34 squared minus 4 times 109, and all of that is over 2. Okay, and then when that's put into the calculator for a simplification, it's a bit quicker to do it that way, you get minus 17, k equals minus 17 plus or minus 6 root 5. And they are the two values of k that where these two straight lines would cross the y-axis. Okay, but having that helps you see that they're about right, because that's a little bit less than 0, and this is quite a bit less with the minus sign, which you can see it would be. Okay, next question. Now we have this slightly unusual question, this logo that's in the shape of all of that really that you can see, and there's lots of information about it there describing what's in the diagram, and we've got to write down in terms of theta the size of angle AOB. Well, you know that there's pi radians in half a circle, so the angle AOB is a half of, because it's shared equally between these two, a half of pi minus theta. Okay, and it says write down, so it's not expecting a lot of working. So for part A, I've just got to write down that angle AOB is a half of pi minus theta, in brackets like that. Okay, now for part B, I've got to find the area. Well, I haven't got to find it, they're telling me what it is, I've just got to show that it is. So I've just worked it through like this. I've said, well, it's a half of 2r, because the radius of this big part of the circle is 2r, half 2r squared theta. Okay, that's that part there. And then I've got two lots of these little bits here. Okay, two lots of those, and those have an area of a half of r squared, and the angle is what I just worked out, half r squared, and it's a half of pi minus theta. Quite a lot of brackets in there, but I'll try and make sure I close them correctly. Yeah, that's right. Okay, and you can put that into the what can we do with that now? That's just checking I've got the right brackets in the right place. Yes, I have. And that gives me 2r squared theta. Okay, 2r squared theta, because that's 2 squared is 4, and then the half makes it 2, plus r squared times, that's a common factor, of half pi minus theta over 2. So it's pi over 2 minus theta over 2. And that gives me, I can take out a factor of r squared and bring this in here as well. So that gives me, so down here, r squared, 2 theta plus pi by 2 minus theta over 2. And that is equal to r squared, because I've got a 2 theta and a minus a half theta, so it's 3 theta over 2 and plus pi over 2 in a bracket. And then I can take out my half, which perhaps I should have done earlier, but anyway, that gives me a half r squared, and then 3 theta plus pi. Okay, so it's just a bit of algebra there, and that's the result that we had to show. Okay, now part C, we have to do the perimeter of the logo, and we got to find this ourselves. So I've just gone around the shape and carefully worked out each arc and the straight lines and just put it all together. So I've got this, the perimeter is equal to well, it's going to be the 4 straight lines, which are, well, we've got 2r plus r plus r. Okay, so there's 2r across the bottom here, and then there's this r and this r here. So 2r plus r. And then I've got 2 lots of the these little arcs here, EF and AB. So 2 lots of r over 2. 2 lots of r over 2 times pi minus theta. And I've also got 2r theta, which is the length of the big arc up here. Okay, and I'm just going to put all that together now, and that gives me 4r from the first part plus r times pi minus theta plus 2 theta. Okay, which is 4r plus r times pi plus theta. Okay, and that I can take the the 4 into the bracket as well to give me a tidier expression, which is r times 4 plus pi plus theta. And that's how it's presented in the mark scheme. Okay. Next question. Question 10. This is about bacterial growth, and we have this exponential model here, and we've got to evaluate the constants a and k to give a complete equation for the model. So we start by using the initial information, and that is that there are 1,000 bacteria at the beginning when t is 0. So that's a e to the 0. So from that, we know that a must be 1,000. Okay, we know that after 5 hours, there are double the number of bacteria. So there are 2,000, and that must be equal to a, which we now know to be 1,000, times e to the power of 5k. Okay, and we can use that to find what k is, because if we basically divide both sides by 1,000, we know that 2 is equal to e to the 5k, and therefore take logs of both sides. 5k is log 2, and therefore k is 1/5 of log 2. So log 2 all over 5, like that. And that comes to 0.139 to 3 significant figures. Okay, now you can use that in all the calculations that follow, and it does work quite accurately, but normally we would carry the natural value throughout the calculation. So I'm just making a note of that there. So the general model is that n equals 1,000 e to the power of log 2 over 5 times the time in hours, t. Okay, so that's the first part of the question in exact form. Now for part B, we are needing to find out the rate of increase at exactly 8 hours. So the rate of increase changes with time. That's the nature of exponential growth. So we need dn by dt when t is 8, dn by dt. So that's simply going to be 1000 times the constant in front of t. So it's 1000 times the log of 2 over 5. Okay, and that's times by e to the power of log 2 over 5 times t. In fact, we'll put times 8 because that's what we know t is. That's what we're trying to work out. And if we put that in the calculator, that actually comes to 420.245. I normally put the answer that I get with a few decimal places just to show that I've worked it correctly and then round it. So to answer the question to two significant figures, 420 to two significant figures. So you're not needing to put units in there, but it would be in bacteria per hour would be the rate. Okay, so that's part B done. Now part C, we have to compare these two models, this one here, which is smaller value at the front of E, but then a larger power. And after a certain time t, both situations have the same number of bacteria. Okay, so we need to set them equal to each other and find what t is. So this is how I would do this question, and you need to be very clear about writing down powers and make sure they're raised up in the air. So I would start by using this new model, so 500 times e to the power of, now if I write the 1.4 as 7/5, okay, and that's 7/5 times the same value of k is used in both models, it says. So that's that times t. So all of that stuff up there is a power of e, okay, and that has to equal 1000 using our model that we discovered times e to the power of log 2 over 5. Okay, log 2 over 5 times t. Okay, now the next thing I would do is take out the, notice that I've got a 500 and a 1000. If I just divide both sides by 500, that's going to give me e to the power of, now I'll do something else as well here. So what I'm going to do is put the log 2 with the e. Okay, so I'm writing this as e to the log 2 and then raising that, all of that to the power of what's left, which is 7/25 of t. Okay, so 7/25 of t. That's the best way of illustrating what I'm doing here. And that has to equal 2 times, and I'll do the same thing there, e to the power of log 2. Okay, and that's now raised to the power of just 1/5 of t, or t over 5, like that, you see. Okay, now I can now remove the log and the e. Okay, so I'm left with this situation that 2 to the power of 7/25 of t, 7t over 25, okay, is equal to 2 times 2 to the power of t over 5. I'll put a bracket round that second part, like that. Now, when I times 2 by 2 to a power, I can put a +1 next to the t over 5 and get rid of that 2. So what I've now got, you see, is 2 to a power of something on the left and 2 to the power of something else on the right, so I can get rid of the 2's. Okay, so 7t over 25, and now I can say that's equal to 2 to the power of t over 5 plus 1, like that, you see. Okay, using the rules of indices. And now the 2's can go, and I've just got to solve a linear equation. So if I put them all over 25, I can now say that 7t over 25, okay, 7t over 25 is equal to 5t over 25 plus 1 over 25, or plus 25 over 25. So basically I've just got rid of my denominators. Probably didn't need to write all that down, but that's just showing fully what's going on. So basically 7t equals 5t plus 25. So therefore 2t equals 25. And if that's true, then t must be 12.5 hours, which is the answer. Okay, so quite an unusual sort of question, really. But you've really got to be confident and careful about using the rules of indices and really understanding them and how to use them effectively. Okay, next question. Now we have here a sum of a series, and it's saying the sum to infinity of that is 9 over 28. So what I'm going to do here is we've got to show that that's true. Okay, and I'm just going to write out what the series would actually look like. Okay, so it starts at 2 and it goes to infinity. So the first term would be 3/4 squared. Okay, so it's helpful to have this in your mind as to what's actually going on. So it's 3/4 squared, okay, plus or minus 3/4 cubed. Okay, now the reason it's minus is because the cos 180n will switch between minus and plus. Okay, if you think of the cos of 180 times 2, that's the cos of 360, you see, which is plus 1. It's the same as the cos of 0. But when n is 3, it's going to be the cos of 540, which is going to be negative 1, you see. So that's going to swing between 1 and negative 1. It starts at 1, it goes to negative 1. But meanwhile, the other part is simply ascending powers of 3/4. Okay, so it's going to be plus 3/4 to the power 4, minus 3/4 to the power 5, and so on. So you've got the idea. Okay, and it's telling us that when that sequence continues, the sum of that, the series, comes to 9 over 28. Now, what I'm going to do is just simply write that the first term, a, is equal to 3/4 squared, okay, which of course is 9/16. That's the first term. And the common ratio is minus 3/4, okay, because what's going to happen is it's switching from minus to plus. So basically, if you take that and multiply it by minus 3/4, you get that. And if you take that and multiply it by minus 3/4, you get plus again, and another power onto the 3/4. So it's as simple as that. So you just now need to use that the sum to infinity of a geometric progression, okay, a geometric series, is equal to a over 1 minus r, okay, which is going to be 9/16. Okay, that's my first term, over 1 minus 3/4. So it's 1 plus 3/4. Okay, and then you just evaluate that, and I'll show the steps, but it's fairly easy to see. So you're doing 9/16 divided by 7/4, which is 9/16 times 4/7, okay, by inverting that fraction, and you can see that that leads you to 9/28, which is the answer that you've got to prove or show. Okay, so it helps there just to map out what the series would look like. Next question. Question 12, all about parametrics, and often with these there's lots of different ways of doing it. My approach was as follows. I took the expression for x and I rewrote it like this. I split the denominator, rather the numerator, into t squared plus 1 plus 4 all over t squared plus 1. Okay, and that enabled me to split that into two fractions, with t squared plus 1 over t squared plus 1 being 1. So it's 1 plus 4 over t squared plus 1. Okay, now that just got a single value of t in, you see, rather than t appearing in several places. So that was part of the thinking behind that. And if I can now do something to that, I can take 1 from both sides. So if I do x minus 1, so what that leads me to was x minus 1, and divide that by 4, taking this down, that leaves me with 1 over t squared plus 1. Okay, and that could be useful because t squared plus 1 appears in the other parameter as well, in the expression for y. So this is the kind of thing that I'm thinking about as I'm going through, and furthermore I can do something else with that, and that is that if I flip both fractions over and subtract 1, I get an expression for t squared, which will prove very useful. So t squared plus 1 is 4 over x minus 1. So t squared is equal to 4 over x minus 1, okay, minus 1. And that's going to prove very useful in just a moment. Okay, so my next thing was to move over to y and look at what I've got for y. Y is 4t over t squared plus 1. So I'll do that from here. So y is 4t, and instead of writing 4t over t squared plus 1, I can write 4t times x minus 1 over 4. Okay, because that is equivalent to 1 over t squared plus 1, you see. So that's already proved useful. So x minus 1 over 4. The 4's cancel to give me that y equals t times x minus 1. Okay, now what I'm going to do now is square both sides, because I need a y squared, you see, and that will give me a t squared, and I have an expression for t squared in terms of x. So squaring both sides, I can say that y squared equals t squared times x minus 1 squared. And I can now replace that t squared with a 4 over x minus 1 minus 1. Okay, so it's just a question of systematically trying to remove the t from the whole thing. So I'm now replacing t squared with 4 over x minus 1 minus 1. So I don't need to square it because that is t squared, but I do need to put that in its own bracket like that. Well, I don't actually need a bracket. What I need to do is put y squared is equal to that. Y squared is equal to that well, and then that needs to be times by x minus 1 squared. All right, it's a bit crowded now, but that's clear enough. Okay, so basically I'm now going to take this x minus 1 squared and put it into this bracket. So I'm multiplying these brackets together to give me 4 times, it'll be x minus 1, because the squared will cancel with 1 underneath, minus, and that's just going to be x minus 1 squared. Okay, so I've just taken this term here and multiplied it with this and by this. Now, hopefully, when I multiply that out, it will give me the equation at the top. So let's see what happens. So what I'm saying at the moment is that y squared, I'm just copying it down here, is equal to this thing here. Let me just make a copy of it for saves a bit of time. So y squared equals that. That's what I've got to so far. Okay, and if y squared equals that, then that is equal to 4x minus 4 minus, and it's going to be x squared minus 2x plus 1. Okay, and that's equal to 4x minus 4 minus x squared plus 2x plus minus 1. Okay, so if I now put my 4x and 2x together, that will give me a 6x, which is encouraging because it looks like I'm going to complete the square. So that's equal to minus x squared plus 6x minus 4 minus 1, so that's minus 5. Okay. Now, if I take out the minus sign from everything, so I'm back to this again, so x squared minus 6x plus 5. If I complete the square for that square bracket, that's the negative of x minus 3 all squared, okay, which will give me a 9 minus 9, okay, plus 5. So where have I got to? I've got y squared equals minus x minus 3 all squared, and I've got minus 4, so it's plus 4. Okay, so that's it, I think, because if I now add this to the left-hand side, I've got y squared. Well, in fact, if I do it in the order they've done it there, that is the last step, isn't it? So I can just add this term here to the left-hand side. I will have x minus 3 all squared plus y squared equals 4, which is exactly what they wanted you to find. Okay, now there may be other ways of getting there, possibly quicker than that, but that seemed to work quite well. Okay, next question. Okay, so this is a trigonometric equation to solve, and again there could be several different ways you could approach this, and this is what I'm going to do here for this one. So let's use the fact that cos 2 theta is cos squared minus sine squared. And by the way, there is a printing mistake. There must be here, because you couldn't possibly solve this with theta there and x there. So I think this theta here should actually be an x. in all cases. Okay, so just bear that one in mind when we come to it. Let's look at this first identity to prove. So I'm going to write 1 minus, and I'm going to replace that with cos squared minus sine squared. Using the addition formulae, but in the double angle formulae format, plus 2 sine theta cos theta. So that's the identity for sine 2 theta. So this is the left-hand side I'm working on, and I'm going to hopefully arrive at tan theta eventually. And then underneath that, I'm going to do a very similar sort of process. In fact, so similar that I'm going to copy it and just change this minus to a plus. Okay, so if I actually took what I'd written on the top line, made a copy of that, put it underneath, okay, all I need to change is that minus sign there is a plus. Okay, that saved a bit of time. All right, now the next step is that I'm going to write this, I'm going to reorder this slightly. So it's going to give me 1 minus cos squared theta plus sine squared theta plus 2 sine theta cos theta on the numerator, and I'm afraid there is quite a lot of this to write down. Now underneath that I'm going to do something similar to that, but it's going to be 1 minus sine squared theta at the front, and then it's going to be plus cos squared theta, and then it's going to be, this last part is going to be the same here. Okay, so that's going to go at the bottom there as well. Okay, so that's the second step, and what I'm going to do now is replace the 1 minus cos squared plus sine squared. You see, that's like another sine squared. So in fact, I could have done this in fewer steps possibly, but that's basically 2 sine squared, because that first part is also sine squared, you see. So 2 sine squared theta plus the rest of it. Okay, so I've got to take that again. Plus that. In fact, I'm going to need it again in a minute underneath there, so I'll put it under there again. Okay, and that's got to have 2 cos squared in front of it. So that's 2 cos squared theta. Okay, and put my fraction line in. Now, the trick now is to divide every term on the numerator and denominator by cos squared theta. Okay, so I'm dividing each term, all 4 of them, by cos squared theta, and that will give me well, you'll see, so that's going to just give me simply 2 tan squared theta. I'll keep the 2's in there for now. So 2 tan squared theta on the top here. This is going to be 2 tan theta times cos theta over cos theta, which is 1. So that's just going to give me 2 tan theta. And then I do the same to the denominator. I divide everything by cos squared. So that's just going to be 2. Okay, and this is going to be 2 sine over cos times cos over cos, which is 2 tan. Okay, 2 tan theta. Okay, now if we look at that carefully, on the top line we can factorize out a tan theta. Well, we can take out all the 2's, and we can take out a tan theta from the top as well. So the tan theta is multiplied by, if I just swap the order around, 1 plus tan theta. Okay, so I've taken out the factor of 2 from numerators and denominators. I've taken out a tan theta from the numerator, and on the denominator I've just got 1 plus tan theta. So you can see now that the 1 plus tan thetas cancel, and it just leaves me with a tan theta on its own, which is what I needed. So that's the right hand side, and that's the end of that part of the question. So quite a lot to write down there for that. So that was question A. Now for part B, I've got to solve this for theta in that, well, for x in that range. So as I say, these should have been x's, and if they were, and you twig that that's what it should have been, then you would simply be replacing all of that stuff with simply tan 2x. So what you would be solving is a simple equation, which is this. So tan 2x would be equal to 3 sine 2x. Okay, now if you multiply everything out by cos 2x, okay, that turns the tan into a sine. So that gives me that gives me sine 2x, I should say. Sine 2x, and that must equal 3 sine 2x cos 2x. Okay, and now I can subtract one from the other to give me 0, and factorize out the sine 2x at the same time. So sine 2x brackets 1 minus 3 cos 2x. Okay, so I've moved everything over to the left and factorized out the sine x. You must do that, don't just lose it, because you'll lose the solution. So therefore, sine 2x equals 0. Okay, which implies that 2x equals 180. Now it equals 0, 180, and 360. Okay, which means that x equals 0, 90, and 180. Okay, but only one of those solutions is valid, because if you look at the limits, neither of them are including. Okay, so we can't use the 0 or the 180. So I will just make that clear in a moment, but let's get all the solutions. I'll just put a little cross there for now, and there, and a tick under that one. Okay, because I'll present the whole solution set in a moment. And now I've got to set a 1 minus 3 cos 2x to 0. So that means that cos 2x must equal 1/3. Okay, which means that 2x can equal any of these values. Off the calculator, 70.528. Okay, I'll just put 70.5 because we only need one decimal place. and also 289.5. Okay, now they're the only ones that will come into range, because x will be half of that, which is 35.3. Okay, and 144.7. Yes, because that was rounded up slightly. I should have perhaps made that clear. You need to be careful about rounding too soon. So that really should have been left as, because it was below 5. Okay, it was 4, 7 something. Yes, and that would cause that to round down to that. Okay, so those are the values of x that we have which both fit the range. So the full solution set be that x equals 90. Well, we normally put them in ascending order, but you don't have to. So let's do that though. So x equals 35.3, 90, and 144.7 degrees. Okay, so quite a lot of work to do, and there often is a lot of work to do on these trig questions. Next question. Okay, this is question 14. We have a curve and a straight line and a region that's shaded between them. And before we find the area of that, which we do need to do, we have to answer part A, which says use differentiation to find the equation of the straight line L. Okay, now you might be tempted to say, well, I know a point there. I can easily find this point of intersection with the straight line and the curve, but you can't use that. You have to use differentiation of the curve to get the gradient of this line. So let's do that first. So basically I can say that the derivative of y dash, is equal to, it's going to be 3x squared minus 20x, and plus 27. Okay, and then I've got to find the gradient when at this point 5, negative 13. So basically when x equals 5, y dash is equal to 3 times 25, that's 75, minus 100, plus 27, and that comes to 2. Okay, now it doesn't look like 2 because it's not drawn to scale, but that's what it is. So we can now use y minus y1. So y minus 13 equals the gradient 2x minus 5. Tidy that up and it gives us y equals 2x minus 23. That's the equation of that straight line. Okay, so we've done the first part of the question and we've given it in the form y equals mx plus c. Okay, so now we have to verify that L meets C again on the y-axis. Okay, well basically we can see that that intersects the y-axis at minus 23. We can also see that the curve intercepts at minus 23. So taking those two obvious things into account, we can simply say that for part B, this is part A, for part B that L and C both pass through the point 0, minus 23. Okay, that's how I would answer that question. Right, okay, now part C, the finite region R we've got to find. So for part C, it's quite a simple, straightforward integration. So we just need to just put a line down there to separate that off. So we just need the integral between the limits of x equals 5 and x equals 0, and we'll make a single function, which is the subtraction of the straight line from the curve. So we're going to do the integral of x cubed, okay, minus 10x squared plus 27x minus 23, and from that we're going to subtract the straight line, which is 2x, and well, we're actually doing minus 2x minus 23, and all of that with respect to x. Now, of course, the minus 23, this will be a plus 23, which will cancel, so that simplifies the process a little bit further. So it's simply going to be the integral of x cubed, let's just write this again, 50, of just the first three terms of that, okay, x cubed minus 10x squared and 27x. In fact, it's with the minus 2x, it's going to be 25x. So we can just do that in one go with respect to x. Okay, and so that's quite straightforward, as I said. So that will give us x to the 4 over 4. It will give us minus 10x cubed over 3. It will also give us 25x squared over 2. And that will be between the limits of 0, 5 and 0. Okay, now we obviously, when we put the 0 in, it's just going to be 0, but let's show that properly. So we're going to have 625 over 4. Okay, that should be 625. 625 over 4. We're going to have, what's that going to be? That's going to be 1250 over 3. And 625 over 2. And then what I'm going to do is I'm just going to I'll put a bracket around that to show that that's with the 5 in, and then I'm just going to put 0 in a bracket to show that I've considered the other limit. And then that's going to evaluate for me to be 625 over 12, which is the exact answer that they're looking for. Okay, so that's that one. Next question. A differentiation. Now, when you look at this, you think, oh, well, we've got to use the quotient rule. Well, you can, yes, lots of algebra to do there. You could use the product rule if you write the 2 plus root x as 2 plus root x to the power of minus 1 next to it, and then do a product. Still a lot of algebra to do. There is another way, of course. If you think back to GCSE, you can simplify y very easily by rationalizing the denominator. So you can rewrite y as x minus 4 over 2 plus root x. Okay, and you're going to times it by 2 minus root x over itself. Okay, now it's really easy because what happens, you'll see in just a moment. Okay, And this doesn't actually feature on the mark scheme as a method, but there's something very similar, which is about a difference of two squares on the numerator. But this is what I would do if I just put some brackets around that, which you really do need. Okay, so that's what I've got. Now, if you rationalize that denominator, it will of course give you 4 minus x on the denominator, which is the negative of something on the numerator. So you lose the denominator completely, which means you don't have to worry about products or quotients and all the algebra that goes with it. Okay, so x minus 4, and you don't even need to multiply that by 2 minus root x because it's going to disappear. In fact, that's the negative of that. So if you just put a minus sign in front of the whole thing, you can cancel those out. But better than that, swap these two over, and that then becomes positive again. So the 4 minus x and x minus 4 cancel with a minus sign. But then if you swap these terms over, you've got that y is simply root x minus 2. And that's easy to differentiate. So dy by dx, okay, is equal to, well, it's the differential of, I'll write it as x to the half minus 2, okay, x to the half minus 2, which is a half x to the minus a half, okay, and the 2 just disappears, and that's therefore equal to 1 over 2 root x, okay, which is much easier than any of the methods, and that's your answer, and capital A is therefore 2. Okay, so always look for processing something before you differentiate or integrate it, because you can often save yourself a lot of time. Okay, next question. Use proof by exhaustion. Now this is where you have to use up all the numbers. You have to do everything it asks you for, so there won't be many to do. And basically, if n is a natural number, it means it's between 1, 2, 3 or 4 basically. So what you have to do is quite literally test all those 4 examples. So let's just do it over here. Let's just start here. So basically the first one you do like this. You say that 1 plus 1, so I'm replacing n with 1 plus 1 cubed is 2 cubed, which is 8, and I can say that 8 is greater than 3 to the power of 1, okay, which is equal to 3. Okay, notice how I'm using the inequalities and the equal signs there, that's fine. Okay, then I can do n when n is 2, so I've got 2 plus 1 cubed, okay, which is 3 cubed, which we know is 27. And I can say with confidence that that's greater than 3 squared, which is equal to 9. And for the next one, I've got 3 plus 1 is 4. 4 cubed is 64. And I can say that 64 is definitely greater than 3 cubed, which I know to be 27. And finally, 4 plus 1 is 5. When I cube that, I get 125. And I can state clearly that that is greater than 3 to the power 4, which is 81. And that's the 4 statements that I needed to show. And just a little conclusion that I can say, therefore, that n plus 1 cubed is greater than 3 to the power n, for all values of n which are members of the set 1, 2, 3, 4, or something to that effect. Okay, so now we go on to part 2, which is a proof by contradiction. So what we've got to do is prove that given that m cubed plus 5 is odd, use proof by contradiction to show that m is even. So what I'm going to do is I'm going to assume that m is odd and it's equal to some number 2n minus 1. Okay, you can either have 2n minus 1 or 2n plus 1. 2n minus 1 where n is a member of the natural numbers, that's the counting numbers, positive integers if you like. Okay, and that's my first statement. Assume that m equals 2n minus 1. In other words, m, I'll say i.e. m is odd. So that's what we're assuming. Okay, so let's process it. So we're going to do m cubed, so 2n minus 1 cubed, okay, plus the 5. That's going to give me 2n all cubed plus 3 lots of 2n squared times negative 1 plus 3 lots of 2n using the binomial expansion or the coefficients from Pascal's triangle, minus 1 squared, and finally minus 1 cubed plus my 5. Okay, that is equal to 8n cubed minus 12n squared plus 6n and plus 4, okay, which I can now show is equal to 2 lots of 4n cubed minus 6n squared plus 3n plus 2. The reason I've done that is I've extracted a factor of 2 as a way of indicating that it's even. So we just need to state there that that's even for all, so even for all members of, for all n that are members of the natural numbers, okay, or the positive integers. And then we want a conclusion, and we also need to say that that would imply that m cubed plus 5 is even, and that's the contradiction, you see. Okay, so we just need to say this contradicts original statement. So my final conclusion contradicts original statement and then we just need to say, therefore, what does it actually mean that it contradicts the statement? Well, it basically means that if m cubed plus 5 is odd, therefore if m cubed plus 5 is odd, then it actually means that m must be even. Okay, let me just move this out of the way. Then m must be even. Okay, so there's a lot to write down on these things. You can't really avoid it. You have to write conclusions and meaningful statements, but try and be as brief as you can. Okay, next and last question on the paper. Okay, this is about the water wheel. This is a modelling question, quite a lot going on here. So we'll make a start on it here. And the first thing we're going to do is express this thing here in the form r cos theta plus alpha. So what we do is we actually expand r cos theta plus alpha first. So r cos of theta plus alpha using the double angle formula is going to equal r cos alpha cos theta minus r sine alpha sine theta. Okay, and we've got to set that equal to 2 cos theta minus 1 sine theta, if you like. I'm just going to put the 1 in there just so we can compare coefficients. So basically the 2, so it is the same as r cos alpha. So r cos alpha equals 2. R sine alpha equals 1. And dividing sine by cos gives us tan. So we can say that tan alpha equals 1/2. And from that, alpha comes out to be on the calculator. If that's the tan of alpha, then alpha works out to be 0.464 radians to 3 significant figures, or 3 dp, and also r is the square root of 5, 2 squared plus 1 squared. So r equals root 5, and our model therefore is that our original expression at the top can be written as root 5 cos of theta plus 0.464. Now we're going to use that in part B, which is about this modelling of this water wheel. Okay, so what we have to do in part B is relate this to what we've got here and adjust it accordingly. So this model shares this part here, the 4 cos and the minus 2 sine, is double this part here. So we can say that h equals 3 plus 2 lots of the model we've just created, so 2 root 5 times the cos of, now instead of theta we're going to put 0.5t, and that's going to be plus 0.464. Okay, now what we've got to do is find the maximum height. Now, because of the fact we've just got one trig ratio here, this makes this very easy to do, because all we need to do is recognize that the cos of something can take values between -1 and 1. So the highest value of this is when cos of that equals 1. Okay, so when the cos of that equals 1, h equals, let me just explain that by saying that. So take a copy of that. So that has to equal 1, which implies that h max, okay, equals 3 plus 2 root 5. And that comes to 7.5 meters to 1 dp. Okay. So that's the first part. Now the second part is asking us about the time at which this occurs. So what we have to do is we have to recognize, when does the cos of this equal 1? Well, it equals 1 right at 0, but it also next equals 1 when this is 2 pi. So basically what we have to do is set theta plus 0.464, okay, has to equal 2 pi. And that gives me that, well, I'm using theta there. I ought to really put the 0.5t. Okay, we can go back to theta and convert it, but it's better that way, I think. So 0.5t plus, that's a plus there, okay, is equal to 2 pi, which means that t equals 2 times 2 pi minus 0.464, and from that you get 11.6 seconds to 1 dp. Okay, so that's when the wheel is at its highest point. Okay, so that's part B answered. Now, to make room for part C, what I'm going to do is the questions here, C and D, I'll remove this stuff now because we finished with it. So I'll just take this out the way and lower it down a bit. Okay, just pop that there. And we will take this to one side because we've pretty well finished with that now. And we'll get straight on with part C. And here we go. So in part C, it's asking about the fact that the paddle will spend a certain amount of time underwater. Okay, and it wants to know how long it spends underwater. So what we're going to do is look at the critical point, the point it enters and leaves the water, and find out what the cos of 0.5t plus 0.464 is at those times. So h would have to be 0. That's the key thing there. Okay, because it would just be touching the water. So that's like the critical value. So that implies that 3 plus 2 root 5, okay, times the cos of 0.5t plus 0.464 equals 0. And you can rearrange that to get that the cos of 0.5, well, the cos of all of this stuff here, okay, is equal to minus 3 over 2 root 5. Okay, and that will have two values that it will return. Okay, and what I'm going to do before I show you that is just rearrange that slightly to give make t the subject. So from that it would mean that t would be 2 times the inverse cosine of, I'll need to put that in a big bracket, 2 times the inverse cosine of negative 3 over 2 root 5. Okay, and there are going to be two values of that, okay, which will be the value where it enters the water and leaves the water, minus 0.464. Okay, and those two values for the inverse cosine of that in radians are, I'll just make a note of them here. Well, I'll show you on a little graph what I'm actually doing, and it might make some sense. So if I put a graph like that and like that to show the first 2 pi radians worth of cos, we know it goes down something like that through pi by 2 down to pi, 3 pi by 2, and then 2 pi. Okay, the two values we get are roughly here, so this is just a sketch, but about this level here, and they are this one is 2.306 radians, and the other one, which comes off this value here, you see, is 3.977. So what we need to do is put those two values in. So we've got that t equals, well, we're going to put the difference between the two, you see. So we've got two lots of 3.977 minus 0.464. I mean, we don't really need to do that because it's going to cancel out each time, but let's just put that in just for completeness. 464. Okay, minus two lots of 2.306 minus 0.464, and that comes to 3.34 seconds, and that's how long the paddle spends underwater. Okay, so that's the answer to C, and then finally part D is just a modelling question. What in reality the water level may not be of constant height. Explain how the equation of the model should be refined. Well, basically, if the water level varies, then the 3 in the original model here needs to change. So the 3 in model would need to vary, would need to change, or something like that. Okay, it's only 1 mark, so it just has to be a pertinent statement. Okay, and that is the end of that question, and indeed the paper. So hope you enjoyed that, and that's taken quite a long time to do, but hopefully it will be of some help. Take care.